Just to confirm, you guys can see my screen.
Sorry?
You see my screen and my mouse?
Yeah.
Okay, cool.
All right. Hi, everyone at the ZX seminar. Today we'll have call comfort. We'll be talking about...
This meeting is being recorded.
Yes, it's being recorded. And he will be talking about graphical algebra and ZX calculus, and apparently all the things he discovered during his PhD. So, Cole, take it away. You should probably unmute yourself.
Yeah, thanks for the intro, John. It's not all of what I discovered during my PhD, but like I wanted to kind of give a broad talk concerning the research I did and also the research that I read and things that I think may be interesting to ZX people that they may not have heard of. And this is the rough outline. So I'm sure almost everyone here knows what the ZX calculus is, but just to like establish notations, I'll give a quick refresher. And then I'll talk about this very related kind of thing, which is graphical linear algebra, and an extension, which is graphical affine algebra. And then what I call graphical Boolean algebra, which is another extension. And then a separate extension is graphical symplectic algebra, which is related to stabilizer circuits. And then I'll talk about all of the related literature, which I don't have time to touch on fully, but I think will still be interesting to ZX people. Okay, so what is the ZX calculus? For my purposes in this talk, I'm going to assume generally that we fix the qubit dimension d, and then we said that the ZX calculus is qubit ZX calculus is generated by these two spiders with phases. So the phases are vectors over the real numbers of length d, and the white one is summing over the standard basis elements. So it's like the Dirac delta, and then there's this phase. And then by the convention I'm choosing is that the gray one, which would normally be like the red spider if you're using colors, you take the Fourier transform of the standard basis, and then you do the same thing. So in qubits, this would be the plus and minus states, or would be the Fourier transform of the standard basis. And what's very important to point out here is that the ZX calculus is universal for matrices of dimension d to the n, but with respect to the Kronecker product. So that to the tensor product, when you draw these string diagrams, so if you take two things and you put them side by side each other, like implicitly what you're doing is, in the semantics, is you're taking the Kronecker product, the bilinear tensor product. And what I'll talk about really soon is algebra using string diagrams where you don't use the Kronecker product. So it's very important to make this distinction. And I'll also talk about fragments of the ZX calculus. And what I mean by that is that these phases here, these vectors, A, I'm putting it here, if you restrict them to have, to be not all vectors over the reals, but have some group structure. So that's, if you do that, that's called a fragment of ZX calculus. And just to recall some basic rules, even though I'm sure you guys all know these, the kind of defining characteristics of the ZX calculus are the spider fusion rules here, and then the algebra rules, and of course there's many more, but just to remind you. Okay, so I said the ZX calculus is concerned with matrices where the tensor product is given by the Kronecker product. But if you want to consider all matrices over a semi-ring or a field or whatever, and you want it to be a prop, so a prop is where you have one type of wire, and by tensoring it with itself, you generate all of the different types of wires. Then you have to actually take the tensor product of the direct sum, because back here we had to choose a d, so we could only pick out the matrices of dimension powers of d. So if you want to get all of the matrices, you only want to have one type of wire. You have to choose the direct sum to be the tensor product. So the direct sum is you take the two matrices and you put them on the block diagonal. So this is a classical result.
Sorry.
Yeah.
So you're saying that I don't understand why universality is important in the previous slide. So you're saying that the one with the Kronecker product, so ZX is universal for Kronecker product?
Yeah, just that you can express any matrix with the type d to the m cross d to the
Right.
n. But for instance, you can't. I mean, obviously, like well, not obviously, but Harney has like worked on this stuff, and you have as well, where you can mix the
Yes.
dimensions, but then it's no longer a prop. So
I
it's
see. Okay,
different
I
colors.
see.
Yeah.
Thank you. Yep.
So the distinction I'm making, at least at this point here, is that yeah, for ZX calculus, you'd have to choose some dimension. So you can only pick out the matrices of a specific type, where the type is powers of that dimension. But here, if we change the tensor product to be the direct sum, then just by taking the one-dimensional vector space and summing it with itself, you generate all of the finite dimensional vector spaces. Yeah, and there's this canonical, or there's this classical result, which is also contained in the literature by Lafont, that this category of matrices under the direct sum is generated by, for every element of the semi-ring or of the field or whatever, you have this multiplication gate. So it takes in one vector or one scalar and multiplies it by a, and then sends out that. And then you have copying, which I denote in white, which just copies a scalar. And this is the corresponding matrix for it. You have addition, which takes two things and sums them. So you can imagine if you put a vector beside this, you multiply, this sums them. And then you have discarding and the unique and the zero. So this is, when people think of matrices, usually they don't think of matrices as possibly having dimension 0, but you need this for the theory to work. And if you impose all of these equations, my references aren't working here, then you get that this is complete for matrices over that field. So this is kind of reminiscent of ZX calculus, although the Frobenius algebra equation, for example, is conspicuously missing. But yeah, if you have all of these generators and these equations, then you can, this is universal for matrices under the direct sum, not the Kronecker product. And here's some example. So the idea is that using these rules here, you can do matrix multiplication and pull all of the copies to the bottom, put the scalars in the middle, and then put the additions on top to get a normal form for matrices. And if you just read this off, this is essentially just reading off the entries of the matrix. So if you put in like a value on the bottom, you copy it, you multiply, you add it, then you get this matrix. And if you factorize it, that's how you do the translation. But yeah, what I also am concerned with here is not just props where there's only one type of generating wire, but I want to add generators that allow you to bundle wires together. So when I do this, I will draw the wire thick. See, whereas here these wires are much thinner, I'll draw them thick. And then yes, if you see this generator here, it takes two wires, one with n wires in it and one with m, and it bundles them together so that now you have n and m wires together. And then you impose these equations. So this is just a way to talk about block matrices. So here you can copy, you can define a copying thing on an arbitrary finite number of wires, as well as addition, and same for the unit, same for the discarding 0. And then in this notation, this is how you can describe a block matrix. So here is a matrix A, B, C, and D. And you define a block matrix where these are the entries. And the idea is basically on the inputs, you copy them, you multiply them by the matrices, and then you add them. And then this is in the correct form of a matrix, like I described earlier up here. Except now it's all thickened, so there's multiple wires going together, and these aren't just scalars, these are matrices. And then if we thicken all of the axioms for matrices, then we can derive these equations which block matrices also satisfy. So for example, matrix multiplication for block matrices. So when I draw these things with capital letters, and it means that they're not just scalars, but themselves matrices. So we first decompose them into according to this rule I gave on the previous slide, and then you unbundle the wires, apply the Algebra rule here, and you copy all of the matrices through the white comonoid and black or gray monoid. You apply more rules, and then you get here this thing. The final step is you sum them, and this is like a graphical way how to do matrix multiplication. And it works for matrices of all dimensions because I've thickened things, so it's not. So this is kind of in itself an inductive argument, which is quite nice.
Quick question, Cole.
Yeah.
Is this, assuming that all of the thickened wires are the same dimension, is this the same thing as just choosing a different ring for your initial what the matrix is going to be over, by just saying that it's going to be the ring of matrices or something like this of that size?
Yeah, maybe, but the only complication would be that usually the semi-ring is required to be commutative, so there might be some technical issue there, but probably that would work as well, right? Because matrices don't commute with each other with respect to matrix multiplication. But I mean, yeah, essentially that's the idea.
Yeah, but it would still be additive, right? So you still have
Yeah.
it would just be a non-commutative ring.
Yep. And also, yeah, it's important to emphasize that these aren't axioms, right? These can be derived, and this is like kind of a proof of one of the derivations. So yeah, but that's the basic idea. Is you go up one level from the ring to the algebra of the ring to the algebra of matrices over the ring. Okay. Yeah. Now this slide is very important, and maybe for some people might not be very intuitive. So I'll try to stress some points. So I just came in the past few slides. I was discussing the prop of matrices, and matrices, or more generally vector spaces and linear transformations. If you think of what is a linear transformation, it takes a vector and produces another vector. But for our purposes, we need something that is not functional, but more relational. So it takes a vector and maybe doesn't produce one vector, but could produce many different vectors. And this is encapsulated by this prop. So the objects are the natural numbers, and then a map from n to m is no longer a matrix, but a subspace of k to the n plus k to the m. And the identity is given by the diagonal subspace. And yeah, this is the point I want to stress that's very important. The composition, so if you have subspace S of k to the n plus k to the m, and T, or this should be G of k to the m plus k to the l, then the composite is defined by pairs of in k to the n plus k to the l, such that there exists one in the middle that is in both S and in T. So the composition isn't like function composition. The function is you're tracing out over the shared elements in the subspaces, which is relational composition. And here again, we ask that the monodal product is the direct sum, not the tensor product. And the tensor unit is again 0. So in particular, you can regard matrices as living within this prop of linear relations. So what you do is you take your matrix A, and then you assign it to the graph, the relation which is the graph of the matrix. So it relates all vectors V to vectors A times V. But also you can do things in the other direction. So if you take the relational converse, then now it relates A times V to V. But no matter which embedding you choose, as long as you are consistent with it, you can see here that matrix multiplication is reflected in the composition of in the relational composition of matrices regarded as relations. So if you have your this relation corresponding to this matrix A and another relation corresponding to a composable matrix B, then just by definition of the relational composition, you're asking for the existence of some k in k to the m such that A times V is equal to k, which is equal to W. But if you just do the simple substitution here, you get that you have the relation V is related to A multiplied by B evaluated at V, which is just essentially the matrix multiplication. So I want to stress the point, this is more general than matrices. So it's not that exotic. You can do all of the normal matrix algebra that you would normally do, plus more. Oops. Yes. And in fact, linear relations are generated by matrices and their converses. So on the left-hand side, I have the matrices. And then on the right-hand side, I've drawn everything flipped upside down, which is interpreted as the converse relation of the matrices. And broadly, there's this pattern here, which is a duality in this prop, which I think is very conceptually important and deep, is that whenever you have something on the left-hand side, which is kind of like knowing that something is true, this functional thing, then this is always dual to asking that the thing on the other side holds. So for example, if we take a function which multiplies by A, then the dual operation is dividing by A. And if we copy scalars, then the dual thing is asking that the two scalars are the same. You're asserting that they must be the same. And taking the sum, the dual thing is dividing the summation into summons. Discarding, the dual thing is existential quantification. So here we're forgetting about all of the x's and relating it to a point. But here from the point, we ask, take any x. And the dual of introducing the zero is kind of like post-selecting or asserting that zero be true. Yeah. And Bunky and all showed that you only need a few more equations, and then this is also complete for linear relations. And maybe now that the Frobenius algebra equations are appearing, then this may seem familiar to some of the ZX people. And I just want to run through a quick example here, just so that people can get some idea of what's going on with this relational composition. So I said that multiplication is dual to dividing. So there's this corresponding axiom here. So how does this play out? So if you first multiply by A and then divide by A, or I guess you first divide by A and then multiply by A, then you, by definition of relational composition, you ask for some y such that the middle thing, the x, such that y is equal to x, which is equal to z. And then you apply the substitution, and then you get the relation that just multiplies both sides by A. But since we've assumed that A is non-zero, we can divide everything by A in this relation and just get the diagonal relation, which is the identity. And what's really cool, in my opinion, about the prop of linear relations as opposed to just matrices is that we can do some linear algebra using only pictures, that if you were to work with matrices, you have to kind of do some sort of exterior reasoning outside of the pictures to talk about. So for example, if you have a matrix from M to N, then, and I'm drawing this in the thickened notation, then if you precompose with this thickened white spider, which is the thickened white spider you interpret as existential quantification, or asking for the existence of a vector of this type, then you have it that it's equal to this set, which is isomorphic to this set, which is just by definition the image of A. And then if you do the dual thing over here, so you take the converse of A transpose, and you precompose with the zero vector, then if you do the same kind of situation, then you get that this is by definition the kernel of A transpose. So by the first isomorphism theorem, the orthogonal complement of the image of A is equal to the kernel of A transpose. At least if you regard them as matrices. Otherwise, it's just isomorphism. But what you can get from this is that by putting this all together, that the orthogonal complement functor, or the orthogonal complement of linear subspaces, extends to a map between linear relations in itself. What it does is it changes the colors. So it sends copying and co-copying to addition and co-addition, addition and co-addition to copying and co-copying, and it sends multiplication to dividing. So this kind of color swapping rule, which is familiar in the Zetics calculus, as the Fourier transform here is actually the orthogonal complement. And this kind of intuitive picture I've been saying, how this looks a lot like the Zetics calculus, can be made formal. And that is that if you take the integers mod p for any prime number p, then this is isomorphic to the phase-free Zetics calculus up to scalars. And the idea is here that if you take your phase-free ZX diagram, so where all the phases are restricted to be 0, and then you look at the X stabilizers, then so the things of this form, for example, for this Z or this X spider, then the stabilizers have the structure of a linear subspace of ZP to the n. And in particular, this thing about generators, scalars being generators, isn't needed here because you can generate all of the scalars just by copying and adding one to itself. Yep.
Just quickly, one slide back, it looked like you had so you have the orthogonal complement for Linrel over a field, but then when you did this in the thickened case, it looks like you're required to take a transpose of the matrix as well.
Mm-hmm.
Because you have AT. Is it the case if you were to extend K to some other, I'm not sure what the equivalent of transpose is for some ring, but for matrices anyway, you just have to take the transpose and you still get the same kind of orthogonality rule, this kind of color swapping, but you have to put in a transpose. Is that right?
Well, first of all, this only works up to for principal ideal domains and higher. So I just simplified this to say fields. So linear relations doesn't even make sense to define composition for rings in general. But I'm not sure if I totally understood the question, but what's important to note here is that the transpose, which I've denoted by this superscript T, is not the same as the converse, the relational converse. So like maybe that's causing some confusion, because I just wanted to put these two things into form so I could state the first isomorphism theorem, which involves taking the kernel of A transpose.
Right.
So,
I just meant specifically, let's just say for the case of matrices over K, then would you get the same thing as the bottom result, but with thickened wires if you also on the right hand side had A being mapped to A transpose?
Oh, I see. Yeah, I think so. Wait, yeah. I think so. Yep. Yeah, pretty much everything that is drawn thin also holds thick, except for commutativity. Okay. Yeah, no, I understand. Yeah, that's true. Okay. Yeah, back to this. This correspondence between if you do the linear relations over Z mod PZ, if you loosen things up a bit so that the maps are not linear subspaces but affine subspaces. So I'm going to label the gray spider with an element of the field A. So here you see A as a constant symbol in the set. So that's an affine equation. Then over the cyclic fields of this is isomorphic to the phase-free ZX calculus plus the X gate. And the affine this affine relation, affine function, corresponds to the f gate, so the x gate. So you can see how kind of like this is reminiscent of the bra-ket notation where the x gate takes a basis element and adds 1. Yeah, and then Bonky and all gave a bit more equations. You can do things like spider fusion, and this is also complete. Yeah, also in their paper, they don't use like phase spider notation. They and they don't even use spider notation, but I think it's much nicer. So I think this is maybe where they could benefit from using ZX notation, for example. Yeah. Okay. So this kind of preceding stuff is maybe at the beginning of my thesis or my PhD experience, what I was reading and thought was really cool and wanted to work on and relate more to the ZX calculus and see if there could be deeper connections that can be made. And there's two kind of separate directions you can go. One is to add kind of phase shift operations, Fourier transform and things like that, and go into stabilizer circuits. And the other is to add nonlinear stuff and to talk about SAT instances. So I'm going to talk about the latter one first. So if you add this generator, this multiplication mod 2 generator, which is like taking the logical and, then on top of the equations of the qubit phase free plus x ZX calculus, except with some caveat that you can't quotient by scalars, so it's not exactly the one I gave in the previous slides. Then you just impose a few more equations. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9 equations. And you also get completeness. And what it's complete for is now matrices over the natural numbers, not the complex numbers. But here where the tensor product is the Kronecker product. So by adding multiplication, you go from the direct sum to the Kronecker product. And somehow from what was the complex numbers before now to the natural numbers. And this is very closely related to the ZH calculus, because you can define this triangle gate, which is the upper triangular matrix, 2 by 2 triangular matrix, this H box, generalized H box, and also the scalar for any natural number n. So I drew these interpretation brackets. And so if you want to go from matrices over the natural numbers to matrices over the Boolean semiring, then the way to do this is to impose either of these two equivalent quotients. So in the ZX or the ZH calculus, people are familiar with this because they can talk about the ZH calculus over semirings. And what this is doing is asserting that 2 is equal to 1, the natural number 2 is equal to 1, is like collapsing it down to the Booleans. So there's been some work in the ZH calculus community on how to encode SAT instances and multi-SAT instances using ZH calculus, but I argue here that this is like the kind of exact setting with no more and no less stuff to talk about SAT instances and multi-SAT instances. So take the Boolean equation, A and B is equal to 0, or A times B is equal to 0, which is denoted by this string diagram. Then if we evaluate the string diagram on all of the possible different inputs, Boolean inputs, then we see that if A is equal to 0 or B is equal to 0, then this string diagram evaluates to the 0 scalar. So that's like a contradiction. Or no, it evaluates to the identity. So it's not a contradiction because yeah, anything times 0 is equal to 0. So that's fine. But if both A is equal to 1 and B is equal to 1, then that evaluates to the 0 scalar, which is like indicating a contradiction. But recall previously I said how the kind of the white spider with one output can be regarded as existential quantification. So in this setting, it's like actually it's asking for the number of it's existentially quantifying over the number of satisfying solutions. So here, if you take the AND gate, you assert that the output is equal to 0. You plug in 2 counting existential quantifiers. We kind of manipulate this diagram along this way and then get the scalar 3. And that means that there's 3 possible satisfying solutions to this side instance here. And as I mentioned earlier, in the work of de Beaudrap and all, this quotient here is precisely the thing that is needed to get you from counting set instances to set instances, because it takes you from here, where the number of solutions is 3, to just 1. However, if there was no solutions, then you would still have no solutions. Yep.
Is this a normal form or something you put it into so that you can tell straight away that that scalar equals 3?
So I put it into like just this form.
Oh, I see.
Just the way that I put it into the way that I represent the H box.
It's successors. It's like a
Yeah,
chain.
yeah. Like I never wrote down rewriting strategy for this, but I think it's essentially the same as you could just take the one that in this paper by you and Neil and Konstantinos, and then just essentially translate it into these generators, and then you'd have the same rewriting procedure.
Yeah.
But this is just you just have no extra stuff, just exactly what you need. Okay. Yeah, so now I said there was a fork in the road, and this is the other fork that I took. And it's not to add nonlinear behavior, but it's to add kind of stabilizer phase space behavior. So here now I have to make the restriction that the qubit dimension is odd prime. And the reason for this is because I want to ask that all of the Pauli operators have the following form. So A is like the power of the pth primitive root of unity, and then these vectors z and x are the powers of the z and x Pauli strings. And for example, in the qubit case, the phases don't have this form because the phases for qubits are powers of I, and I is a primitive 4th root of unity, not a primitive 2nd root of unity. But what's really nice about this, if in all of the odd prime dimensions, is that if you have 2 Pauli operators, which I've labeled by vec z and vec x and vec z prime and vec x prime, and if you push them past each other and you commute them, then this phase pops out here, and the phase here is determined by, there should be an omega in there. The phase here is determined by the symplectic form, which is, it takes the z and x and takes the inner product and subtracts it with the other z and x inner product. And Pauli operators are said to commute when no phase appears. And here that means that when you evaluate this symplectic form on the two vectors corresponding to the Pauli strings, but it's equal to 0, because if you take e to the power of 0, that's just the identity. So it does commute in just the normal sense of what it means to ask for something to commute. Yeah, so if you ask for a maximal set of mutually commuting Pauli operators, right, I said in the previous slide that all Pauli operators have this form, then this determines what's called a stabilizer state by taking the joint projector onto all of these subspaces determined by these Pauli operators. So you take the scale, you normalize things by the number of times you're taking the sum, and then you project onto this Pauli operator here. And in the language of symplectic geometry, this this maximally commuting set of Pauli operators determines what is called an affine Lagrangian subspace. So now if you just work over any field, you can define this as the affine subspace is S of k to the 2n such that it's equal to S omega, where S omega is the set of things that commute with each other in the sense that I described in the previous slide, right? Where this omega value is to 0. And asking that S is equal to its own dual in this sense is asking that it's maximal, which is a requirement for the projector to be a pure state, which is a stabilizer state. So in some sense, there's this duality. You can regard a stabilizer state in odd prime dimension as an affine Lagrangian subspace, and it's just thinking of the state in Hilbert spaces versus the structure of its stabilizers.
So what is it that breaks if you have not a dimension that's not odd prime?
It's this thing here, the e to the 2i times a over p, because that's not Pauli operators don't have this form for p is equal to 2, because e to the 2 pi I times a over 2 is -1, not I, which is what you need for qubits.
Right, okay.
For example, and similar things arise in even dimensions. In odd but non-prime dimensions, things work, but it's just annoying, so I'll just ignore them. But yeah, I think it all just works in all odd dimensions, and then the prime ones are just easier to work with, but the even ones have this problem with the phase at the beginning. Yeah.
So cool.
Yeah.
This definition of stabilized state, on the next slide, the definition of stabilized state, or I say determined stabilized state. Since this is a sum of Pauli projections, it's not obvious that this would be a rank 1 pure state, right? But will it always be?
Yeah, so it's only a pure state if this set is maximal.
Yeah.
Because you can just do some argument about some kind of combinatorial argument about the rank of things. And yeah, so if it's not maximal, then it's not going to be a pure stabilizer state, and I'll get to that in a moment. Yeah, but okay, I said that if you take the affine relations over the field of cyclic integers, or the integers mod p, then you got phase free set x plus the x gate, which is the affine shift. But here, if you double things, so now where the maps are not just affine relations, but they're these affine Lagrangian relations, which I described here. So the maps are affine Lagrangian subspaces. Then you can generate all of the things in the following way. So now you'd have these two spiders. Now each spider is labeled by 2 elements of your field. And the first one is an affine shift, and the second one does this multiplication. And if you have these 2 spiders, so now every wire is like kind of has 2 wires grouped together living inside of it. And you also have this one, which multiplies by the one wire and divides by the other wire. Then this generates all of the affine Lagrangian relations. And this is up to scalars isomorphic to stabilizer circuits in odd prime dimensions. And some kind of intuition for this is that the Fourier transform, for example, if you decompose it into the Euler decomposition, then what this looks like is it takes the 2 internal wires, multiplies one of them by 1, and then swaps them. So the colors, since the colors are on the opposite sides of the wires for the Z and the X spider, then this swapping is like the Fourier transform, because it takes the gray thing on the one side and the white thing on the other side, and then moves them around, and then multiplies by 1. And if you have a Pauli here, which is Z to the A, composed with X to the B, then the idea is that it it adds the shift on the Z operator to the first wire. So this is this affine shift by A, and then on the X, the shift in the X operator on the second wire. So you can kind of think of the one wire as like the Z stabilizers, the first one, and the second wire is the X stabilizers, and together these two wires muddle up, kind of carry all of the stabilizer information of a stabilizer circuit. And yeah, so one way to think of this is you take these affine relations, which I described a long time ago at the beginning of this talk, and you augment them with more phase information. So you take your white spider, which was like copying and co-copying, and now you add, you embed this into the white spider where everything is 0. And then you take your affine shift here, and then you embed this into the gray spider where the A is identified with the poly X phase. Right here, this one on the second wire. Yeah, in a paper that we really ought to put on the archive very soon, then reminiscent of the paper of the Z extravaganza paper, where you have these generators that you have completeness for odd prime dimensional stabilizer circuits. Over any field, you just essentially do the same thing using this kind of algebraic way we've defined things, and you get completeness for all affine Lagrangian relations. And here is a way to think of them in a geometric way to think of them, which I think might be useful to people. So these affine Lagrangian relations are the oriented volume preserving transformations. So what does that mean? It's if you look at the unitary things, what preserves oriented volume? Shifting does. So if you take a poly X and a poly Z, or more generally just the spiders like this, then the X shifts this oriented area up, and the Z shifts it to the right on the plane. And then if you apply this multiplication gate, recall here, it multiplies the X by A and divides the Z by A. So what this results in is this kind of squeezing thing. Because the volume of this parallelogram has to be preserved, when we multiply the X by A, the Z has to be divided by A. But the volume remains the same, and the orientation remains the same. And you can also do shearing has the same effect. Shearing preserves volume. So if you take top and you can just drag it along, shear it with A, then it has the same volume. And the Fourier transform is some kind of reflection, which also preserves the volume and orientation, for example. And so those are the unitary things. But for example, for the states, if you have a state in the Z basis labeled by AB, then you can think of this as the relation which takes a point and relates this point to every point on a line where the line is determined by the curve x is equal to b z plus a, right? So the angle between this line and the origin is given by the inverse tangent at b, and there's an affine shift by a. So the b is the phase shift gate, corresponds to the angle, and a corresponds to the affine shift on the how far it is from the origin. And similarly for the X spider version, you're doing the same thing, but now the shift is now in the X direction rather than the Z direction, and the angle is now measured between the X line and not the Z line. And then if you were to take their adjoints, so the effects, the similar effects, then what it would do is it would take the line and relate only the points on the line to a point, and then everything else is undefined. So really, these phases are lines, and the things between them are the transformations that preserve volume. Yeah, and also I should mention that in physics, this is kind of a general way in which you talk about the conservation of the conserved quantity between position and momentum is given by volume. So this is a more general thing than just talking about stabilizer circuits. So there's a way to add, so to touch on, I think it was John's question, there's a way to add discarding to things. So in this paper by Carret et al., they gave a graphical way to add the quantum discard, or the maximally mixed state equivalently to circuits. And if your circuits have, if your prop has enough isometries or enough co-isometries, then you can just freely discard all of them, and that is equivalent to giving you discarding or the maximally mixed state. So here, these are the isometries, and if you add these equations, you get discarding and you get the maximally mixed state. And what's particularly nice here is that the discard relation, like as a relation between sets, as a linear relation, is the same thing as the quantum discard. So the idea is that you have this requirement that everything has to be maximal to define a stabilizer state. And if you loosen this requirement by discarding things, then you get a projector without rank 0, which is like a mixed thing. And the way to think of the maximally mixed state is you take a point and you relate it to the entire plane. Or conversely, you take the entire plane and then you relate it to a point for the discard. And yeah, if you do this, you do the same kind of trick, the same kind of thing, then this gets you the prop of affine coisotropic relations, which is like essentially just mixed stabilizer states. So here, I've weakened from asking that S is equal to its dual to just asking that it includes its dual. So this is where the maximality is like weakened. Yeah, and there's two ways to think of the Steinspring dilation. The one is in terms of the linear subspace. So you can say that any affine coisotropic relation is the image of a Lagrangian isometry, or an affine Lagrangian isometry. And what is the image? The image is to precompose with this relation here, right? Or for the Steinspring dilation, you can say that every mixed stabilizer state can be dilated into an isometry. And these are both this different views of the same thing, this coisotropic reduction and the Steinspring dilation. And so in fact, this is how you can kind of recover the notion of an encoder for a stabilizer code, because you think of the stabilizer code not as necessarily as an isometry or a mixed stabilizer state, but you think of it in terms of the code space, and the code space is the image of this isometry. So it's a linear subspace. You think of it more of a linear subspace usually than you think of it as a linear map, but I mean, they're equivalent. So that's kind of cool. Yeah, but so that I've kind of described some of the work I did in my thesis, but I want to talk a bit more about other things that I think people should be aware of that may be interesting to them. Yeah. First, here's some kind of open problems. Yeah. So for this ZX calculus with the AND gate, the normal form is given by reducing polynomial equations over this ring. So you have a bunch of polynomials, indeterminates. Modulo is ideal, saying that x squared minus x is equal to 0. So x squared is equal to x. But to generally execute it, so you have to do this thing. So modulo the ideal by x to the power of d is equal to x. And so if you want to get a qubit generalization, this would be a lot harder, because you don't have this nice equation that p of x times q of x is equal to 1 if and only if p of x is equal to 1 and q of y is equal to 1. So like if someone could figure this out using Grosvenor basis would probably be the right way to go about it, but Grosvenor basis, modulo, and ideal. Or more generally, could you have some sort of graphical algebraic geometry where the maps are, you know, maybe more general ideals over a ring, maybe nothing to do with finite fields. This would be really cool if somehow the ZH calculus maybe could shed some light on algebraic geometry. Oh yeah, and I said that symplectic geometry preserves these oriented Euclidean areas or volumes. Because you take these 2 points, the symplectic form gives you the area of this parallelogram, where this point here is the wedge product of the 2 points, which is equivalent to 2 times the area of this triangle. So you can ask similar questions. What are the similar string diagrams? What are the relations between the string diagrams if you change the notion of volume? So if you make the phase space to have constant positive curvature, then now you're working in hyperbolic geometry. So the area would be kind of like this, or in parabolic geometry where the curvature is negative, the volume would be like this. So you can ask similar questions. What would be the kind of stabilizer ZX calculus, but where the phase space has some curvature? And this is a concrete problem which could just be calculated. And maybe there's applications for this in physics, I'm not sure. Oh yeah, and finally, there's other kinds of graphical algebra where you take the subspaces to be different kinds of structures. So there's this graphical polyhedral algebra. So now the maps don't have to preserve parallelograms, but the maps are themselves polyhedra. So I've just taken a picture of polyhedra from Google Images, and Bonnke and al. Gave a complete set of equations for this. And it's very, very similar to the Zeiss calculus, except the generators are slightly more rich. And in a similar vein, there's also this graphical piecewise linear algebra by Boisseau and Pirou, which refines or generalizes rather graphical polyhedral algebra. So now instead of just being polyhedra, the maps can be piecewise affine subspaces. So I've drawn a very crude piecewise affine function here. So the question is that I have, maybe someone else finds interesting, is can these more general kinds of props where the maps are different kinds of algebraic structures, can this be used for quantum computing or physics? Because a lot of physics studies group representations, because group representations are the kind of language of symmetries in linear algebra. So if you take different group representations, you ask for a different type of subspace, could you kind of just get some analog of the ZX calculus? Maybe not, that's not interpreted in Hilbert spaces anymore, but has some sort of physical meaning. Because it seems like this is a very flexible kind of way of thinking about the ZX calculus, which is not dependent on Hilbert spaces as a semantics. Yeah, so discuss different props where the maps are kind of subspaces that have some extra structure. Yeah, group representations. Can the subspaces be kind of correspond to group representations in some sense? Is there more to do? Can we talk about more exotic physical things? And I want to give some references to interesting people. So I talked about graphical piecewise linear algebra, graphical polyhedral algebra, graphical affine algebra. So these all look a lot like ZX calculus, but have slightly different semantic or very different semantic domains. Interacting Hopf algebras, which is the graphical linear algebra. And then there's this advertising this forthcoming paper by Robert and Titouan and I. Also, yeah, there's stuff on the discard construction, and then some of my work, this paper by Neil and Alex and Konstantinos, and the very closely related ZX extravaganza paper. Yeah, that's my talk. Thank you for listening.
All right, thank you, Cole. People want to clap in their own way, whatever way you want on the Zoom meeting. Yeah, it is 4. So Cole, if you have to go, I understand. But if you want to stick around and maybe answer some more questions, then that's also fine by me.
I'm not in a rush.
All right, any questions?
Yeah, I have a question. So this upcoming paper with Robert Booth, the point is you have a completeness where you don't need to sort of unfold the Lagrangian relations into this doubled picture anymore. Is that the point?
Yep.
Okay, so you kind of do it all at the level of these kind of spiders, which are labeled by pairs of field elements.
Yeah, or another way to think of it is you do the Z extravaganza stuff, but from with the different semantics in mind.
Mm-hmm.
Do you have to consider fleximetry in the upcoming paper?
Yeah, the upcoming after because Titon and Robert are very much fleximetry fans. The paper will be fleximetric.
Okay, so you still have to have fleximetric constructions if you want it.
I mean, you don't have to. It doesn't have to be fleximetric.
Yeah, right.
But then you can represent things as undirected graphs. And maybe to tease a little bit that sure that everyone knows that the QDIT ZX calculus can be flexsymmetrized, or the QDIT phase-free ZX calculus can be flexsymmetrized. But say linear relations over a field in general can't be flexsymmetrized because of the scalars are not generated by summing one. So, but in this like in the affine Lagrangian relations, actually this extra structure overcomes this hurdle, and then it can still be flexsymmetrized in all cases. So to me, that was kind of surprising how, despite linear relations or affine relations in general not being flexsymmetrizable, where you can only for the finite fields as a special case, or prime fields as a special case. Yeah, when you shift when you add the Fourier transform, then this allows you to flexsymmetrize.
That's
and
very
I hope,
cool.
I hope that Robert or Titon could give a follow-up talk next semester. So I also tried to introduce some of the stuff that would be needed to understand the contents of the next paper. Yeah, like this kind of scalable stuff, and you can talk about the kernels and images of things using pictures. So that'll be very important.
I was also thinking, so this ZX Clifford QOPIT calculus is kind of like two-dimensional shapes or transformations there and vectors. And then if we would put there Clifford plus T, because if we have a power of 3 in the in the power of E, then we have Clifford plus T's, right? So then we could imagine those as three-dimensional transformations.
Well, the problem there is that it couldn't be linear anymore, just because of a counting.
Right. Yeah.
Counting argument, because here the tensor product is the direct sum, so it'd have to be. Yeah, to do this, you'd have to somehow drop linearity. So I'm not sure what the semantics would be, but if you could find something similar, that would be very cool. But yeah, just because if you just count the number of possible states, then it can't possibly be linear in a three-dimensional sense anymore.
All right, thanks.
All right, do we have any other questions from the audience?
Maybe a quick one. Which the answer could just be no. Have you had any new ideas about qubit stabilizer?
No.
Okay, it's a quick question.
Yeah, I don't know. It seems like a lot of. Well, I've had some ideas, but the idea when I think too much about it, then I'm just like, oh well, yeah, maybe that will work, but the amount of effort it will take is just not worth the juice is not worth the squeeze. But I think I have an idea of how to do it, but like I haven't done any calculations because I don't want to be bothered.
Cole.
Yeah.
What do you mean by orientation preserving in the symplectic geometry bit?
Wait, where did I put this? Here. Wait. Yeah, I can't. I lost my slides, but where did they go? Yeah, I think I had a typo. The Fourier transform is not like a reflection. It's a rotation. But I can't go to the slide anymore because wait, maybe I'll stop my share and then reshare. Yeah, I think I made a typo. The Fourier transform shouldn't be a reflection. It should be a rotation.
Okay, yeah, I see. Yeah, other than that, it makes so that's what you mean by orientation preserving, no reflections.
Yeah, it's that yeah. Like you could have, for example, negative you can have like a volume and then like a negative volume, but those are not the same as each other.
Yeah, okay, that makes sense. Yeah, thanks.
You just like imagine this volume here and then the points are all back here. Then even though they have the same volume, that you consider the volume to be a vector. Yeah.
Okay.
I have one last question, maybe, or one question. So you mentioned application to physics. Have you looked into how this applies to continuous variable photonic stuff? Or is it unrelated or
Oh yeah, very, very much related.
Related, yeah.
Yeah, like I guess the general idea is that replace the field, the finite field, to a field of characteristic 0. And then you have to do a bit more work, but you know, like these terms like squeezing, for example, come up in photonics. But this, I mean, if you just do this over the reals, then you get kind of some infinitely squeezed continuous variable thing. And to talk about non-infinitely squeezed things, you need to do a bit more work, which is what we're working on. Because, you know, this line is like infinitely thin. So you need to make it not infinitely thin to have it be a state.
Yeah, okay. Yeah, the physical states.
But the transformations are the same. You can still do shearing and reflection or rotation, I mean, and squeezing. But the states and the effects can't. This is like a non-physical thing because there's no physical line with no width. But yeah, that's the basic idea.
Is this something corresponding to homodime and heterodyne measurements of these Gaussian states?
I think I'm not
Okay, that's fine.
not
don't worry.
100% certain, but I think kind of this idea of angles I think that the idea of angles has to do with homodyne and holodyne measurements because you kind of want to have a homodyne measurement would be like a line that is completely straight up or completely side to side, but it may have to be kind of fuzzed up a bit because this is like an exact. Oh, I guess that is the homodyne measurement I think would be kind of a projector onto like either a vertical line or like a horizontal line, and then some of the holodyne measurements could be captured by having rotated lines, but not all of them because you need to do more wacky nonlinear stuff to get the ones that would give you more power. But yeah.
Very cool. Also here, it kind of suggests that if you set A to 0 in both of these X and Z states, then they will be the same.
When B is equal to 1.
When P is equal to 1.
Yes.
Right, yeah, that makes.
I think that is in your guys' paper. I think that's.
So we have some correspondence between the two, but the relation between the X and ZB is a bit more complicated. It's like minus B to the power of -1.
Minus B to the power of -1.
That
So
might be
B
because you have
inverse.
the taxometric thing.
Oh yeah,
Yeah.
possibly.
Yeah, that's only that's because you're interpreting because of the arc tangent of if you think of this as a 45-degree angle, like I didn't think of theta as being pi over 4, then it doesn't matter if it's going through the origin. It doesn't matter if it's pi over 4 from the X or from the Z. It's the same line. So I think in your guys' paper it's just some antipode thing.
Yeah, right. Very cool. Nice.
Pi by 2,
Thanks.
right? Yeah, pi by or no, pi by 4. Pi by 4, sorry, you're right.
Yeah, pi by 4, yeah. I guess also you could do with other angles as well, but that would be just one. And also something that's kind of cool is you can have like thinking of things this way, you can have like an angle that is completely vertical or completely horizontal because you have these two different spiders. But if you had only one, then at the asymptotes wouldn't exist. So you need both.
Thanks.
Okay, if there is no more questions, then let's thank Cole again. Emoji. Yeah, thank you very much. We will be here next week.